let's resume our discussions. So in the last lecture, we talked about the memory array efficiency, and this is an indicator of how well the design is. So ideally, you want to maximize the area occupied by the memory cells instead of the peripheral circuits. So today we are going to see some real examples with the real silicon data to further take a look at this array efficiency. So this was an example from Intel 32nm processor, and it was launched in 2010. So it was a while back, but still at that time you see that it has two versions. One is with 6 core, one is with 2 core, and then the 6 core processor has more than 1 billion transistors. This was like almost 14 years ago. So here in this design, you see that it has 3 cores, and then you have the L3 cache, which is shared. And here are some details of the L3 cache. So here, each individual SRAM cell occupies this 0.171 micrometer square silicon footprint. And then it operates on 2 VDD, depending on the operation mode, active or for the standby retention mode. And then for the L2 cache, which is within the core, then you see that each SRAM cell will occupy a larger area. This is what we discussed before. There's a trade-off between the access latency and then the capacity, or in other words, the integration density of the SRAM, depending on the levels of the cache. So for L2, then the total size is like 256 kilobytes, and then you do use larger cells for faster operation. So here, let's take a look at this 6-core processor in more details. Here are some data sheets for this 6-core processor. Again, L3 cache, 12 megabytes in total. And then the total die size, that means the total processor silicon footprint is 240 millimeter square. And this includes the logic core and then the memory controller for the DRAM control, and then the L3 cache. So here, let's look at the L3 cache only. Okay, let's focus on the L3 cache only. And then we want to estimate what is the array efficiency for the L3 cache. So from the information from the previous slide, we can calculate this actually as a back of envelope calculation. So here from this die photo, we can estimate the L3 region. You can use ruler or whatever method you prefer. It's about 26% of the total die size. Okay, if you look at this L3 region. And then the die size is given in the previous slide. So here the total die size is 240 millimeter square. So this one times 240 millimeter square, then that will be the L3 cache silicon footprint. And then the array efficiency by definition is SRAM cell size for individual cell times number of bits or number of SRAM cells, and then divided by the chip size for the L3 cache. And then the chip size for the L3 cache we just calculated is this 240 millimeter square times 26%. Then here for the SRAM cell size, if you recall the previous slide, we say that it's 0.171 micrometer square per cell. And then how many cells are there in the L3 cache? 12 megabytes, okay? And then 1 byte equals to 8 bits. So in total, you have 96 megabits. So that's the number here. And then each cell is this 0.171 micrometer square. So you do the calculation, you plug in the numbers, and then you will get a rough number that is about 27%. So this is pretty low in this case. this is a rough method to estimate the array efficiency from the given information from the data sheet. So any questions here? Okay, so the SRAM array efficiency is on the lower end. And then for the DRAM and NAND, you will see like 60% or even 80%. So let's look at other designs. So here, this is a POWER9 microprocessor from IBM. And this was published in 2017 ISCC. And this was fabricated in 14 nanometer SOI FinFET technology by Global Foundry. You know, IBM has a partnership with Global Foundry. And this processor has 8 billion transistors. The total chip size, die size, close to 700 millimeters square. And the clock frequency is pretty high for this one. This is for high-end, high-performance computing environment. This was deployed to the national lab, the Summit and Syria supercomputer system in the Oak Ridge and the Lawrence Livermore National Lab. And the supercomputers are made of those IBM's POWER9 processor, and of course with NVIDIA's GPU. So here for this processor, let's take a closer look. So each CPU die has 4 cores, and here you see the actually more than that. Okay, so each CPU actually has many of those quad. Actually, it has like 6, and then each quad has like 4 cores. So here are some more information. So each core here has like 32 kilobyte L1 instruction cache and L1 data cache. So for L1, the cache has 2 types, like instruction and data So then here every 2 cores share a L2 cache, which is 512 kilobytes. And then the L3 cache is huge in this case, 120 megabytes. So I have to point out that here the L3 cache is not SRAM in this particular example. So here the L3 cache is made of eDRAM, embedded DRAM. So this is a unique design with IBM and Global Foundry because they have this particular process for the embedded DRAM, which is based on 1 transistor, 1 capacitor, embedded DRAM process. And 1T1C, of course, will be smaller than 6 transistor SRAM as a Zen technology node. That's why they can greatly shrink the cell size for the eDRAM cell you look at here. Even for the dense SRAM cell, for the like their L2 cache is about 0.1 micrometer square, and then eDRAM is like more than 5 times smaller for the cell. So that's why they can pack like 120 megabyte L3 cache here. So this is a unique design, and we will talk about the eDRAM when we move to the DRAM sections. So then let's look at some recent examples. So this is from AMD Zen 2 microarchitecture. It was fabricated by TSMC 7 nanometer FinFET process, and this was disclosed at ISCC 2020. So here, this is used in the commercial, the Ryzen 3 processors. And here you see that it has 4 cores. And then within each core, it has a 32 kilobyte L1 cache, and also split between data and the instruction. And then you have the 512 kilobyte L2 cache here. And then the L3 shared among multiple cores, in total 16 megabyte L3 cache. Okay. So here is a closer look at the L3 cache. And this L3 cache, it has been split into 4 like block. They call 4 slices. Each is like 4 megabytes. And if you look at within one slice, it also has the data and the tag and the control and so on. So this prefer logic. And then if you look into the core, which contains the L1 cache here, if you zoom in, also the L2 cache, you can see here. So here, I think this L1 cache is split between those two. The instruction and data, those are the L1 cache. And then you have other logic, like your ALU, and then floating point compute, and then some like branch prediction for your, computer architecture kind of control. So this is how it look like if you zoom in to the core. So again, most of the silicon area occupied by the L3 cache. You look at this one, right? L3 cache by itself is already more than 50% of the total processor's core area. So here are some summary data for this Zen 2. And I will not repeat. So L3 cache 16 megabytes. And also it discloses some of those design rules for the lower level transistor level design rules, like CPP, contact poly pitch. This is the distance from the source to the drain. And then the fin pitch, because it's FinFET process. And the metal one pitch. So those are the key indicators for the logic transistor's cell density. And then it uses 6-track standard cell library. That means there are 6 metal one track within one standard cell library. And then in total, it uses like 13 metal layers to finish the routing for the interconnect. So here, this is the latest offering from AMD. So SRAM is entering a new era, 3DV cache. This was introduced in Zen 3 and also the Zen 4 architecture announced this year. So here, AMD pioneered in the 3D stacking for the cache. And here, this is the schematic. So basically, they have a separate die, which is reserved for the cache only, L3 cache only. And then in this case, this top die has 64 megabytes. And then under that, it has 32 megabytes cache on the base die with the cores. So you still have the cores here. And then here is the L3, but it's within the base die. And then you have extended L3 on the top die. And then they stack, okay, using the bonding process. So you have 2 dies and then bond together. And both dies are fabricated in TSMC 7 nanometer, and then TSMC did the bonding for AMD. So in total, you will see a huge, like 96 megabytes. So you can read this paragraph. So built on the same 7 nanometer process, and then the extended 3D V-cache die, and then it's sitting on top of this on die, which means on the base die, 32 megabytes L3 cache. But from the CPU cost perspective and from your software, your instructions, we'll see in total 96 megabyte addressable L3 cache. So there's no difference, okay, from the software point of view to differentiate the 32 megabytes or the 64 megabytes. So they will see the entire space, which is 96 megabytes. Instead of as opposed to that, the 64 is viewed as L4 cache, like additional layer of the cache. So both the top die and bottom die will operate at the same CPU frequency. Okay. So this is the new trend for the SRAM cache. As you can see, the 3D integration will continue the Moore's law scaling, right? If 2D scaling ever stops, then you have to utilize the third dimensions to stack more and more transistors. So any questions here?
Often the base we need to communicate with each other, right? So
yeah.
Like the speed, like because since it's like stacked vertical.
So the hybrid bonding has very minimal parasitics, according to AMD. So the top dies will have some like 4 CPU clock latency to transfer the data, but it operates on the same clock speed. But you just need to wait for 4 cycles to fetch the data from the top die, and that's it. Yeah.
The previous chart you showed the different parameters, right? In that, what is the F that you were talking about in the area?
You mean the array efficiency for this one? Previous slide.
This, what is the F that we were talking about?
What is the F? So here we'll discuss that more, maybe in later lecture today, or maybe next lecture. So this F definition is very tricky. I will talk about that maybe later. So I just hold your question. Okay, so then SRAM is also widely used in GPU, right? So here, this is the NVIDIA 7nm A100 GPU, and it has in total like 87 megabyte SRAM as well. But if you look at GPU architecture, it's different from the CPU. So GPU has many cores for the parallel, operation. So NVIDIA called it as SM, stands for Stream Multiprocessor. Basically, it's a key computational unit within a GPU. You can think it's a small core, okay? And in total, it has like, I think has hundreds of those small cores. Okay, and here, yes, 108 of those small cores. And within each small core, you see that here, this is zoom in to each of this small core. It has L1 cache, or again, instruction and data. And then also you have some register file, like a 256 kilobytes. It's also kind of SRAM, okay? And then here L1 data cache is also 196 kilobytes. So basically on the order of hundreds kilobytes each core for L1 cache. But you have many cores. So in total, the L1 cache in total is already like 47 megabytes. But they are very parallel. Right? You have many of them. And then it only has L2 cache shared, like 40 megabytes among those cores. So the overall architecture is very different from the CPU, as you can tell, right? So then it has many of those small cores, but each small core has hundreds kilobytes L1 cache. Okay, so then let's look at the DRAM. This is the first generation of the DDR5, the 5th generation of the DDR chip. This was announced by SK Hynix 2019. And it is built on this 1Y load, the second generation of the tens of nanometer DRAM process. And then here it has a data rate 64 gigabit per second per pin. We'll talk about that more when we talk about the DRAM. So here you look at the DRAM array. It has maybe like tens of banks, and then the peripheral logic only occupies some of those, So DRAM dies are very organized, right? So then the most of the memory cell will occupy those space, and then only the lighter color represents the peripheral circuits. So DRAM also enters a new era because of the 3D integration. So DRAM's latest movement is to form this HBM, high bandwidth memory, which is a key enabler for the GPU product today. NVIDIA benefits significantly from this HBM. So here, this is the latest product, as you know, H100 from NVIDIA. And it contains 6 HBM. So here, they are co-packaged. So this is the core, GPU core. And then you have 6 HBM stack. And each stack, I believe, is 8 DRAM dice vertically stacked. So in total, you have 96 gigabytes DRAM capacity. And each HBM is 16 gigabytes. And you have 8 of those DRAM dice stacked. So each of this is like 8 of the DRAM dice vertically stacked. Okay. So you can and look at more details from the data sheet. But I just want to highlight the memory component here, 96 gigabytes DRAM in total. And it's the 3rd generation of the HBM. And then the total bandwidth is like 3.36 terabytes per second. That's the bandwidth you fetch the data from the DRAM to the GPU. So any questions here? We'll talk about more of those DRAMs later when we move to the DRAM section. But here just some, heads up about the latest product on the market. So the NAND, okay. This is the 2D NAND scaling from 2008 to 2014. So here the last generation of the 2D NAND is at this 14 nanometer node. And it has like 128 gigabits capacity per chip. And then after that, the NAND Flash transition to the 3D NAND because 2D scaling stops at this point. So this happened about like 10 years ago. So here you see the NAND bank also, let's say they call it a plane. Here it has 4 planes. Each plane is like 32 gigabits. And in total, you have like 128 gigabits for the entire chip. This is the last generation of the 2D NAND. We will talk about more on the 3D NAND when we move to the NAND Flash section. Question?
Why did the scaling stop here? Because after 14 nanometer, we could go lower.
Yeah, there are many challenges. We will talk about them more. Yeah, just hold that until we, talk about the NAND Flash. Basically, you cannot scale due to many of those, either from the geometry or from the electrical, from the coupling between cells, and also retention and so on. Many factors. Yeah. Okay. So here, this is a quick summary. So memory, you can find it in many places in the VLSI system, right? So here, the demand for memory is ever increasing because of the big data and AI, ML workloads. Is all memory funded application. And the NAND Flash has become the mainstream storage media, from your SSD to your SD card to your USB, and also in the data center for the storage. And the DRAM is really the key enabler for the GPU. And SRAM is also making steady progress with the 3D V-cache kind of innovation. So this will help with with last level cache in the CPU as well. So the array efficiency is a key metric to evaluate the memory chip design. And I have to say the memory industry, especially for the DRAM and NAND Flash, is cost, and cost, especially for the NAND Flash. So the reducing the cost per bit is the ultimate goal for the memory industry. Okay, but for DRAM, maybe you still care about the bandwidth, but for the NAND Flash, then the cost is a key. Okay, any questions before we end? All right.